This is actually an interesting set of compounds that I'm going to bring up. Before joining Simulations Plus about 5 months ago, I worked in the medchem CRO space, and I was working with a company called Edelris in Lyon, and they have some really interesting molecules and interesting chemotypes that are inspired mostly from natural products. And so when I told them that I was transitioning to Simulations Plus, they were kind enough to say, well, if I asked actually, I said, would you have most of the compounds they don't disclose, but I said, would you be kind enough to provide me with a set of compounds that we could potentially use in demonstration scenarios with clients. And so the CEO, my boss, Jean-Yves Ortolan, kindly said yes and gave me a few files. And so this is where these compounds came from. There are some pyrido oxazepinones and related compounds thereof, and you will see immediately what I mean by that. So and when you load them, you see that that you've got the identifiers, you've got the you can expand that to see the actual full ID of the compound, and then you've got a distribution of molecular weight, which sort of gives you a sense of the size of these compounds over on the right-hand side. So one of the pretty cool capabilities in the software is there's actually a few different sub-series of chemotypes within these 500 compounds. I think there's 500 compounds. Yeah. So there's actually a few classes within that. And one of the things that actually thought was pretty impressive is that the software was actually really efficient at finding those classes in a way that would take a little while by eye to figure it out. So they're mostly a core plus R group type setup. So I brought up under chemistry, you have this option that says generate classes, and there's a few algorithms that allow you to essentially cluster your compounds into families. Since we're dealing mostly with core and R groups, or exclusively with core and R group, I chose the ring anchored systems as the clustering option, and that will take into account that I mean, this is the kind of compounds we're dealing with. So if I press here on the OK, it's actually pretty fast, and you see in your main spreadsheet here a class list. So C2 means class number 2. There's 132 compounds in that class. C1 has 299 compounds. So every compound in the spreadsheet is assigned a class. Now if you go...
also with this method, I think some compounds can be put in more than one class. I doubt if it happened here, but it's
I don't think... Yes, so these are your classes. I'll show you there's actually some pretty cool functionality here. What you notice is that there is... So this is the pyrido oxazepinone class 1 and class 4, 1 and 4, and they're ordered by how many compounds are in each class. So basically the most populated cluster is at the top, and then the least populated clusters are at the bottom. You'll notice that this scaffold here in blue is a regioisomer of the one on top. What is kind of murkying the waters a little bit here is that they're not oriented all the same way. So what I'm going to do is bring them up and show you how you can align these correctly so that it just becomes a lot easier to look at them. So if I double click on this, you will see see it in this orientation, and you can actually do a quick cleanup. Okay. And then what I probably want to do is actually flip it vertically. Okay. And that actually probably shows it in the orientation that pretty much everybody would want to see it. And so when you like it, you can use this black arrow here to transfer it back where it came from. Okay, so you hit that and it say, do you really want to do this? And I say yes, and you will see it come into the picture right there. Okay, and we can do the same. We can kind of realign these kind of the same way. So if you hit the rotate button, which is this circle over here, then you can grab any point and actually rotate it correctly, and then same thing, send it back to where it came from, and suddenly it's aligned correctly. You can do the same thing for this one. Here we go, more or less. This is going to facilitate looking at these compounds and these series in a way that is consistent. And I'm going to look at the fourth one. We're going to do the same thing. Basically, and say, yes, I'm happy with this, go for it. So now we've got these scaffolds in a proper proper orientation that we can actually look at them and compare them, and you will see that the proper substructures are highlighted in blue, and that you recognize the regioisomers in each case of the pyridoxazepinones, series 1 and 4, and then the sulfonamide analogs, which are series 2 and 3. Okay, so that's that. Now what's pretty cool is that when you go, if you want to propagate that alignment to the compounds themselves, all you do is you do a right click and you say align compounds. Okay, now if you go back to your compounds list from class 1, you will see that they're all aligned in the orientation that I put them. And of course the other ones are not, because I haven't touched them yet, right? Okay. So we can do that for all of them. So align compounds, right click, align compounds. And now, miraculously speaking, they're all aligned on, they're not scaled the same because they're of different, altogether some are bulkier than others. So it's the size varies, but the orientation of these compounds actually remains the same. Right? Does that make sense?
Yeah. Mm-hmm.
Okay. So one of the things we can do now is this is really kind of the preliminary thing, just to make things look good, and it just, I think everybody in the medchem, would kind of want to look at these compounds in a consistent way, so you can tell, oh yes, there's an R, slight difference in R group over here. Otherwise, it makes the comparison of the compounds really, really difficult. So now what we're going to do is we're going to calculate ADMET properties for all these compounds. So we're going to go and calculate ADMET properties. I've got a few user models in there. We don't need to use these. One of the things in the software actually is that the descriptor calculation is really fast, and so it actually takes about the same amount of time to calculate one class of properties versus everything. So you may as well just calculate everything. And if you're ready to proceed, just hit the calculate button. I don't have a super fast machine, but I think it's still a Core i7 laptop. But it's still done in just really literally pretty quickly. So it outputs the profiles for the properties for each compound, and so these pie charts basically give you, for each one of these molecules, for instance, for CYP substrates, it gives you the status, whether or not it's a substrate for CYP2D6, 3A4. That's at the individual compound level that it's doing that. That's interesting. One of the things that you can notice is that it actually gives you that information also at the level of the class. And that's what gets really interesting, because suddenly you can see that some classes behave very differently from others, that there is at least predicted to be some CYP specificity with the sulfonamide analogs, and that there is really, whereas the other ones are pretty much the standard or normal pyridoxazepinones are basically picked up by everything. These are based on averages. I was actually not completely sure initially how the software handled it, but we went through it, and it's actually putting averages for classes. And for all the properties, you have averages. So I can go here and look at the, for instance, let's pick an interesting property for, I think solubility was there, yeah. Solubility may be a really interesting one to look at. We see that this one, class 4, is the least soluble one. 1 and 3 are the most soluble. It's a solubility expressed in mg per mil, and class 2 is really not very soluble. So it's pretty interesting because it gives you kind of a general trend in each class. So you can start looking for trade-off, and I'm looking for ADMET code and ADMET risk. So this is actually a really important column here. ADMET risk is the overall risk as kind of a combined score across the different liabilities that are identified across the compounds. And again, these are going to be averages across each chemical series. So the one with most liability is actually series 4, then series 1, then series 2, and series 3 has the least. So this can actually be a really interesting metric in terms of balancing the size, how many compounds you'd want to have in each class, right? This is a breakdown of the risk, of the ADMET risk here, in terms of tox, in terms of do we have the ADMET risk separate?
That was it. Yeah.
Oh yeah, that's it.
ADMET risk, then ADMET risk, absorption risk,
absorption risk, etc. CYP risk. So if you have again a completely different chemotype, the risk is probably going to come from a different feature, but the overall score is still comparable. Does that make sense?
And I think, to put it on total equal footing, if you had R1 and R2 substituents on each one of these scaffolds, and all of those were the same, and so you had all the same, side chains and everything, then it really does come down to the property of the scaffold rather than the ones with the side chains. And even in that case, I think I think that would be more definitely an even comparison. But the scaffolds also can influence things like metabolic risk because they'll have different log Ps, and that'll bind different to the enzymes.
Yeah. But like here we see that really in terms of CYP substrate specificity, I mean they're really very different.
Yeah, that was interesting. Yeah,
it's very interesting that how those problems can be solved. Now Well, what's interesting too is to balance the, balance the number of compounds that you're contemplating making in each class. Based on that, you can revisit. Now, all of these cells that are, if you want to explore, say, one particular compound in detail, for instance, solubility. Everything that's grayed, if you double-click, it will show you a solubility profile as a function of pH. Okay.
Right.
So I don't know if you've worked with that at all. The other thing I should mention is that when you have a value that is underlined in red, it means that it is outside of the bounds of the training set for that particular model. So it's basically, take that prediction with a grain of salt, because it may not be an accurate one. Doesn't seem like we have too many here, but that could be one. The other thing I wanted to show is the pKa. I wanted to do a quick jump into the pKa for some of the compounds that have ionizable groups. So, for instance, this one here, if you double-click on this, you will see the different species, which we call microstates, that make up this particular compound. And then you can also, if you click over here at the top, the ionization start, you will get a sense of the population, how the population changes based on pH. So, and we go here. That's actually pretty nice. So at physiological pH, 7.4, or essentially it's almost entirely in the the form that we have it shown over here. So non-ionized form. Knowing that in the GI tract, actually at lower pH, it could potentially change. So and then so anyway, those are some of the things that you can do. Now,
just want to talk about classes. If you could click on the classes tab one more time. So if you've got something highlighted like this one, and you go kind of straight up, where the MedChem Studio tools are, Eric, just go straight up. Okay, so that section of tools right there are for the MedChem Studio module. And the furthest one on the left, go all the way, click that. That will, go ahead and click it. That will transform all the compounds from that set or class into the Compounds tab. Okay, so now you're in the Compounds tab with just those 10. Okay, and so if you go back to the classes, now by default, what we're displaying is the representative structure. That is the lowest molecular weight structure. If you go under, I think the classes menu, let's see, menu, drop-down menu, and then let's see, it would change representative structures, kind of near the bottom. Yeah, right there, click on that. Okay, so the default is the minimum value of molecular weight, but you could do solubility, you could do IC50, you could do PIC50, you could do anything that's in the spreadsheet, essentially.
You wanted the most soluble one.
Well, you just selected the least soluble.
The least soluble one, okay.
Because see on that dialog box, there's a, do you want to display the maximum or the minimum value? Okay, there you go.
Most soluble in the chart. So if you go here and you select water solubility, so S plus SW, and you click on the use log X scale, then you will see that on a log. Otherwise, it's pretty difficult to. The other thing I was going to show you was the R tables, because for each one, when you select this one and you go to R tables, it's showing you the breakdown of the of R groups for this particular set of compounds. Okay, so here in this class we have 299 compounds, I think. Yeah, 299, and what you can do is actually, if you wanted to have access to the entire matrix, because this is a sparse matrix right now, right? There's 2 R groups for R1, 13 for R2, 4 for R3, and 25 for R4. 24 by 5 is 100, times 13 times 2, that's 2,600 compounds in the full matrix. But here we have just basically an exemplified subset. So one of the things you could do actually would be to go back to the entire superset of compounds that that you could make, across all of these combinations. Do you see what I mean?
Mm-hmm. Yeah.
Because this is just a sparse matrix. It's just an exemplified subset of compounds. So it will actually allow you to export that. I think it's under R tables. You can say explode products, right? And then you can browse here and say C1 all, for instance, and C1 underscore all 2600. And say save and OK. It's telling you it's estimating 2,600 compounds, and now you're basically generating the entire 2,600 and bringing them in ADMET Predictor. Right. So now this is the full set of the 2,600 compounds, and now you can refine your analysis. If you wanted to select from the full matrix, you can do it from that. Okay.
Yeah.
Does that make sense?
Mm-hmm.
Yeah. So I can show you a few more things there, I think. And what's kind of interesting here is when you have this column, which is called product in class, all the ones that are exemplified actually have an EDX ID. The ones that don't have anything, that are that have an empty column here, are not exemplified. So those are potentially new compounds that we haven't made yet as part of the exemplification set.
Right.
Yeah. So I think what I can do here is Control A and create new class. Now we've got so I'm basically redefining the scaffold, very quickly redefining the scaffold, because it doesn't have that, it doesn't know that right off the bat. So I redefine the scaffold, and then I can get the complete R table now for those compounds. Okay. So this is the complete R table of now, instead of 299, we have the full 2,600 compounds with the core highlighted in blue. Okay. And that is on the right-hand side, your distribution of molecular weight, I believe. We can do the same. We can go back here and recalculate all of our properties. So this is going to take a little bit of time, but we do have a little bit of that. I think it's interesting to go back and potentially optimize a selection of compounds, for instance. We're going to probably go simple and say bias a set towards more soluble compounds. But if you wanted, you could create, say, a composite function that incorporates more than one criteria and then optimize on that. So say you identify a certain number of issues in the complete set, and you want to make a subset of compounds that is, again, sort of focused on a better set of ADMET properties, you could then do that using that tool. So So that's pretty cool, and we're going to do it. I think we're going to do it in that chart on the right here. Once it's done with the calculation, what we'll do is we'll do what we did before. So we're going to represent solubility and see if we can draw a more soluble subset from these 2600 than what we had before. So we have that. So let's display solubility here, S plus SW. Here we go, and we're going to put it on the log scale so that we can actually read it. And now if we go to our R table, believe in design, you can do find subset using R groups, and you have within that you have a button that says find best subsets. Okay, so you can click on that, and it's asking you which property you want to use to optimize. So we're going to do solubility. We're going to stand by our word and say we're going to do it on solubility. Let's take the elevator a little further down here. Here's our solubility parameter. Larger values are better. That's what we want. 260 compounds is a lot, so I think we'll just say, you know, MedChem, we tend to be a little bit more conservative than that, so we'll say we want 100, and we're just going to say OK. And now what you'll see here on the right is that we have highlighted in red the selected set of 100 compounds. The scale for the distribution for counts is different on the right and on the left. So on the right here you have the scale for the subset. That's why it's a smaller scale. And on the left you have the scale for the unselected. Okay, so you can see what we've done, that we've totally biased our selection towards a better set of compounds. And then you can go over here and say, hey, show me the set of R groups that are necessary to make that set of compounds. So R1 and R2 are fixed. Those are the green ones. And R3 and R4 are full. Okay, so 4 times 25 is 100. That's what we asked for. And R1 is hydrogen, and R2 is over here. All right, so that's kind of in a nutshell some of the, you know, so very MedChem-oriented practical features that I wanted to share with you. Have been, you know, trying to, you know, visualize, you know, how one would work with that kind of data set and do some potentially useful, you know, MedChem reasoning as far as potentially boosting or reducing certain subclasses, and within each class finding compounds that are potentially better than say the average compound that you'd find in the class, you know, bias it by whatever, you know, set of properties you think are most desirable. So that's in a nutshell what I wanted to go through.